So what we're going to do is take those properties of inverse functions and apply them to our graphs of sine, cosine, and tangent. So in this video, we're just going to look at sine. So we'll kind of go through these properties and this new notation, and then we're going to apply the same thing to cosine and tangent. So in this video, I'm going to try to explain a lot with it, but then when we get to cosine and tangent, it might go a little bit more quickly because we would have gotten through some of those pieces. All right, so we've been working with sine of x. We've been finding values with it, mostly using the unit circle. We've also thought about it in terms of a right triangle. In fact, let me draw a picture for that. So in terms of the unit circle, what we've been doing is on our circle, we'd be given some angle that was showing up inside of the sine function. In this case, it's showing up as x, but you could also think of that as some angle measurement. And on the unit circle, what that came through as is that would tell us where we were landing. And then we were looking at that coordinate that was on the unit circle to get the value for sine. That was the y coordinate there. So I'm just going to highlight that. So we grabbed the y coordinate. Pen malfunctions here. Come on. Highlighter. There we go. That's all I wanted to do. So given some angle measurement, sine of that angle measurement was equal to the y coordinate on the unit circle. So in terms of input and output, that was the idea that the input was some angle, and that angle could be in degrees or radians, and we're going to kind of switch between the two. Generally, if you're not sure which one to use, this is typically going to be radians. Something we're going to start seeing is mostly when we work with the unit circle, we're going to be describing things in terms of radians. If we're working with triangles, so some more kind of geometric ideas, then that'll be in degrees. But typically for most of this, we're going to be in radian mode. All right, then the output for that function was the y coordinate on the unit circle. Another way we thought about this was with a triangle, a right triangle specifically. So if we had some right triangle and some angle measurement, and knowing where that angle measurement, we had opposite, adjacent, and hypotenuse. What sine would do is that given that angle measurement, so plugging in that angle measurement, then what we could do, I'm just going to write an alternate into this, is that we would take opposite over hypotenuse. So it'd be this ratio of opposite over hypotenuse on that triangle. So that's another way of thinking of the output for this function, is that it's equal to this ratio on a triangle, not ration, of opposite over hypotenuse. So that's what we've been working with so far with our trig functions, is given an angle measurement, either going to the unit circle and grabbing a specific coordinate, or looking at a triangle and using these ratios of side lengths. All right, so inverse of sine, which is how I would read both of these. So there's two notations here, and both are correct. You're going to see both in your work that you do. So with that, I'm going to kind of keep switching between the two notations just to emphasize they do the same exact thing. So they work the same way. So this first notation just has that symbol of -1 like we saw in the previous video. So that's inverse sine of x right there. However, this other notation, so arc sine is how I would write that. So arc sine, rather, that's how I would say that, is the same thing. It's also representing the inverse of sine. And I will say in my work, I typically use arc sine mostly just to avoid that thing that I mentioned in that last video of being careful of not thinking that's an exponent, because that's just such a common mistake with these. But with this notation, it just really emphasized like this is an inverse function. This operates differently than just sine of x. So you'll see both of these notations as we go through our work. So making that inverse function, what's going to switch are the input values and the output values. So how this function is going to operate is the input for the function is going to be the y-coordinate on the unit circle, or some ratio of side lengths, or ratio of opposite over hypotenuse. And the output for the function is going to be the angle measurement. So our original sine function was the idea of given some angle, finding that y-coordinate. Now this one is going to be given that y-coordinate, we're finding the angle measurement. So for these, we're solving for an angle. Whereas here, we were solving for that y-coordinate. So that's how these are going to switch around. And basically when you come across questions where you need to find an angle, you're going to be using an inverse trig function. That's what these are all about. In fact, I can make that a little note up here. Inverse trigonometric functions solve for an angle. That's what we're doing here. All right, so with that in mind, we've looked at our inverse function. We have an idea of how it's going to work in terms of input and output. However, if we look at the graph for our function, what we're going to see is we've failed the horizontal line test. However, we have this whole section on inverse trig functions, so we're not just going to stop there. So like I showed in that last video where we looked at the parabola and how the parabola in its kind of full form was not invertible. However, if we restrict the domain of that original function, we can make it invertible. And that's exactly what we're going to do here. What we're going to do is just look at part of sine. And the idea is we've kind of looked at problems similar to this. If I draw my unit circle here, we've looked at problems in our class where maybe we were given a value for sine, so we knew our y-coordinate. Let's say I was here at positive 0.5. The idea is that we had two possible solutions. We could be over here in the first quadrant or over here in the second quadrant, and then part of the problem's work was to figure out which quadrant we were in. The issue with this is in terms of a function, this isn't operating like a function. A function is for every input, there's exactly one output. And this is a case where we had our input of that y-coordinate, but the output has two angle measurements. So that's where we need to restrict the domain of what we're working with here so that we know, are we in quadrant 1 or are we in quadrant 3, so that really there's only one output and we're not juggling these multiple outputs. Okay, so I'm going to get rid of that for a moment. So going back to this graph, restricting the domain. So what I'm going to do is I'm going to think of starting at the origin here, and then I'm just going to go kind of reading to the right until I would start failing the horizontal line test, which is at that maximum that I want to stop, because if I continued on here, then I would immediately start failing that horizontal line test. So I want to stop right there, which is occurring at pi over 2. Now I can include more of the graph if I had gone to the left. These have unique y values. I would be passing the horizontal line test here, 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 until I reach that curve. I don't want to turn that curve because if I drew over here, then I would start failing that horizontal line test. So I want to end right there. So if I just take this kind of snippet of sine, for that, I would pass the horizontal line test there. I just can't continue on beyond those values. However, this little window here, captures all of my possible outputs for sine. I can see all of my possible y values spanning from -1 to +1 are captured in that window. So the idea is going to be that maybe sometimes we land in an angle measurement that's outside of that window, but we can always trace it back to inside the window. We can get there if we have this certain, really it's going to work that we have this certain output. So like if I was at positive 0.75, I can trace it to an angle that's in this window from -π/2 to positive π/2. And even though there are solutions, other solutions out there, like this would also have an output of positive 0.75, but that angle measurement is outside that window, so we wouldn't have that as a solution. Our solutions will only show up here. So for this, we have our restricted domain, which means we calculate inverse sine of x. I'm going to write it as arcsine, only for angle measurements from -π/2, and we're going to include those endpoints to positive π/2, or -90 degrees to positive 90 degrees if we were working in degree measurements. So what that means in terms of our unit circle is that when we go through these cases where we know our y-coordinate and we want to find the angle measurement, the only possible solutions are going to be on this part of our unit circle, working from -π/2 to positive π/2. Which means in terms of possible terminal sides, like we could have a terminal side down here, so we'd be looking for that angle measurement. And notice that we have to be within this domain here, so between -π/2 and positive π/2. So when I'm looking at this terminal side, I don't want to measure it by going around the circle, so getting something larger than 3π/2. That goes outside of this range. Instead, what I would want to do is go in this direction. I would have some negative angle measurement, but we want that kind of shorter distance rather than going all the way around. And if we're in the first quadrant, we just do it as we usually do, of in that positive direction. Okay, so let's look at some examples that now we have all this information. So how are we actually going to solve these? So what we have here is we're looking for some angle measurement. And what we have here is a y-coordinate on the unit circle. Those cases up above where I mentioned the right triangle and opposite over hypotenuse, we'll look at examples with those, but it's going to be in cases where we're looking at an actual triangle. Most of the time we're going to be on the unit circle. So let me draw a sketch of what we're doing here. So we're looking for an angle measurement. And that's really what this is saying. It's saying find our angle measurement given that we have this y-coordinate of -√3/2. Now, as soon as I see that we're working with an inverse function there, I want to think about limiting the part of the unit circle I'm looking at. I want to only be on this part of the unit circle. So when we look at √3/2, that's going to relate to angle measurements with a π/6 increment. So we have these key coordinates we're used to, like √3/2 and 1/2. Those often work together in positive and negative forms, and with angle measurements that are increments of π/6. Similarly, we also have coordinates like √2/2, and that's going to relate to increments of π/4. So seeing that I have this √3/2, what I'm thinking about in terms of my unit circle are the possibilities would be these increments of π/6, but only in this window from negative pi over 2 to pi over 2. Now I can see that the y-coordinate is negative, which is going to force us to be actually in this third quadrant here. So those possibilities that I drew up above are actually not possibilities, and I would be down in this fourth quadrant. I typically write out both of the coordinates just to kind of organize it in my head. So for this first one, the x-coordinate is long and positive, so root 3 over 2, and the y-coordinate is short and negative. And then this one here has short positive, long negative. And I'm looking for the coordinate that has y equals negative root 3 over 2, which is happening right there. So my angle measurement is right here. So solving for the angle, what I'm going to do is, and like I mentioned up above here, we're going to go in the negative direction. Because if I go all the way around, let's see, that would be 1, 2, 3, 4, 5 pi over 3, where we could see that there is this angle 5 pi over 3. I don't want to use that because it's not within negative pi over 2 to pi over 2. So where we have that angle measurement, it's not actually my solution. Instead, what I want to do is go in this direction. Go in the negative direction to match up with that domain that we're working with. So with this, let's see, 1, 2, so that's going to be a negative pi over 3. So that would be our angle measurement that we would plug in to get that y-coordinate of negative root 3 over 2. So our solution in solving for this inverse sine of negative root 3 over 2, that's exactly equal to the angle measurement negative pi over 3. Similarly, you can always look in both forms, like this is the inverse form. We could go back to the original form of how we would work with sine. It's just when we work with just sine, the input is the angle measurement. So sine of negative pi over 3. And if we look at the unit circle, we would get that y-coordinate of negative root 3 over 2. So you can kind of see it in both forms. However, the form we're working with, this is the solution we want to have. Now, if we go to the calculator real quick to double check our answer, you can see sine, cosine, tangent there. If you go to this functions tab, you can see the inverse functions there, and I'm going to switch this to radian mode. So what we could do is that inverse sine, negative square root of 3 over 2. And we get that value out there, which might not make much sense to us, but if I plug in negative pi over 3 there, I can see it's a match. Similarly, I could have typed in arcsine, just type it in on the keyboard, and of that negative square root of 3 over 2, and it does the same exact thing. So you can use either form. I think usually if the keyboard's easily accessible to me, I just type it in instead of going searching for the button, but either way will work. All right, so that's our process for solving here. We're going to be working with this function. It's just kind of reverse of how we've been working with our unit circle. We've been plugging in an angle and getting the y-coordinate. This one, we're searching for that y-coordinate and then figuring out the angle measurement that matches up with it. So let's do one more here, inverse sine. Again, with this one, so we want to find the angle measurement where we have y equals negative root 2 over 2. So in terms of my unit circle, and what I do is I just immediately kind of highlight where we have to be on that side of the unit circle. We can't go to the other side because then those inputs and outputs don't work for us. Now, y is negative, so it's going to tell me that I'm actually down here. So I can be a little more specific with that. And then root 2 over 2 is going to line up with our increments of pi over 4. So that should be occurring right there-ish. There where we have positive root 2 over 2, negative root 2 over 2. So there we're seeing that y-coordinate that we want to work with. So that angle measurement there, we're going in the negative direction, and that's a distance of pi over 4, negative. So this arc sine of negative root 2 over 2 is equal to negative pi over 4. All right, so that's the setup for our inverse function, the idea of solving for angle measurements and working with the unit circle, just kind of switching operations. So we're going to do this through cosine and tangent as well, which should go a little more quickly because it's really going to be the same process as we did for this.